Hello and welcome to today's presentation. My name is Kengo Oka and I'm a Principal Automotive Security Strategist at Synopsys. I work with OEMs and suppliers in the automotive industry globally to help them develop more secure software. In today's presentation, I would like to describe practical steps for fuzz testing embedded software in a CI pipeline, a continuous integration pipeline, and also go through an example implementation. On today's agenda, we have 3 points. The first point is on challenges with fuzz testing in the automotive industry, and we'll discuss a little bit about the common challenges. The second point is on the strategies for enabling fuzz testing in a CI pipeline. And then the third point is on the practical steps for integrating fuzz testing. And we'll go through an example implementation at this point as well. So let's start with the first point and go through some of the challenges with existing fuzz testing in the automotive industry. Before we begin, I would like to give some background on the automotive trends. There are 4 major trends in the automotive industry, often referred to using the acronym CASE, which stands for Connected, Autonomous, Shared and Services, and Electrification. Regarding connected, we see vehicles today with more connectivity and more communication interfaces, including Wi-Fi, Bluetooth, V2X, 5G, etc. Regarding autonomous, we see autonomous vehicles where we have advanced systems controlling the steering, braking, and acceleration of vehicles, as well as a number of different systems with sensors, cameras, radar, and LiDAR that process the input regarding the surroundings of the vehicle. In addition, we have a number of new services, including services provided in the cloud by OEM backends using web apps or mobile apps. And finally, regarding electrification, we see a trend towards electric vehicles, EVs, with new technologies such as charging and battery management systems and V2G. These automotive trends lead to a need for security. As briefly mentioned on the previous slide, these 4 major trends, connected, autonomous, shared and services, and electrification, require more software and also create more attack surfaces, as well as generate more valuable data, both on the vehicle side and on the back-end side. Thus becomes more lucrative targets for attackers. Therefore, there is a need for cybersecurity. This is already recognized in the automotive industry with the upcoming regulation UNR 155 on cybersecurity, as well as the ISO SAE 21434 cybersecurity engineering standard, and the recently released Automotive Spice for cybersecurity. And both in the ISO SAE 21434 and Automotive Spice for cybersecurity, fuzz testing is mentioned as a recommended test approach. One thing to note about fuzz testing is that to achieve better results, it is better to execute fuzz testing as much as possible. For example, continuously in a CI, continuous integration pipeline. First, let's go through what we mean by fuzz testing. Fuzz testing is a test technique where malformed or out of specification messages are provided to the target system, the SUT, system under test. And that system is then observed for any unexpected behavior. If there are any unexpected behavior, it's possible for developers and testers to further analyze the issue and detect unknown vulnerabilities in their systems and components. On this slide, we see an example system that's communicating over Bluetooth. There are fuzzed messages sent over Bluetooth here, where typically on the screen you would see the song title, the album name, and the artist name, but because of the fuzzed messages, it's only displaying null. You can imagine if it's possible to craft a malicious message that would, instead of just showing null, could potentially take over that application and execute arbitrary commands. So let's take a practical look at a fuzzed message. Here we use the Posix fuzz testing tool and the TCP for IP4 test suite. As you can see in the top portion of the slide, we have a set of different test suites. Right now we're looking at the TCP test suite. And within the TCP test suite, we have a number of different fuzzed messages. This example here shows the different fields in a TCP message, where we can see that the source port and the ACK number, for example, contains anomalies. We can then send these fuzz messages with these anomalies to a target system and observe how that target system would respond to these messages. Let's take a look at a simplified CI pipeline and try to understand the problem of trying to include fuzz testing as part of the pipeline. As a first step, we see here on the left-hand side, we have our build step. In this step, we can use various solutions, such as static code analysis and software composition analysis, that can process the source code as it is. In the next step, we have our flashing, where we connect to the hardware device. And this is typically the first challenge we have, that testing will then be performed on hardware. We need to flash our binary to a hardware device, a microcontroller, or a ECU. And often that test target, the standalone ECU, is running by itself. So we have a limited test environment, which is also a challenge. And then finally, we have to perform our dynamic testing. And this includes the normal functional testing that we typically do, but also we want to add fuzz testing here as part of the pipeline. And this is the second challenge we have. If we include fuzz testing at this stage of the process, it occurs late. It needs to be done dynamically, which means it requires the binary to be executed. And this typically means that the testing occurs late in the process. So with this understanding of the challenges for integrating fuzz testing into the CI pipeline, let's take a look at some of the strategies that we can apply in order to successfully integrate fuzz testing into a CI pipeline. Regarding the strategies for fuzz testing in a CI pipeline, we have a number of questions we have to ask ourselves. We see here on the left-hand side a number of questions, and we'll go through these one by one and explain a little bit about how these questions can be addressed. The first question is on when to test. So the important thing here is we want to test as often as possible, as much as possible. So shift everywhere is really the key word of making sure that fuzz testing occurs as often as possible when it's available. So examples include, for example, off-peak hours. You can perform testing during nights. You can perform testing over weekends. So making sure that you use any time available to perform testing. The second question on how long to test, we want to make sure we can use the full amount of time available as efficiently as possible. So if we have time to perform testing, let's use that time, the full time available to perform that testing. When it comes to what to test, it's important that we perform a TARA, a threat analysis and risk assessment, to identify the high-risk interfaces and target applications, so we know what are the high-priority targets that we should test. Regarding how to test, we need to understand what is the best environment we can use. For example, can we perform testing on native Posix, or can we use virtualized emulated environments such as QEMU? Or do we require hardware interfaces for certain hardware components such as Wi-Fi, Bluetooth, and CAN? Next, regarding how to detect exceptions, we have to understand how we can monitor the target system. For example, using in-band instrumentation, where we monitor the same interface that's being fuzz tested. Or if we need external instrumentation, where we use some kind of external means to monitor the target system. And finally, how to manage test results. Here we have to understand how we can log failure conditions on the target system, how we are able to reproduce the issue, as well as have some kind of criteria where we can decide whether we need to break the build based on the results of the testing. So based on this general view of the strategies for fuzz testing in a CI pipeline and understanding the type of questions that we have to answer, let's move on to the third point and discuss the practical steps for integrating fuzz testing and also go through this example implementation. The practical steps for integrating fuzz testing into a CI pipeline involves 4 steps. The first step is understanding the existing CI pipeline. Here we need to understand what are the stages of the pipeline and when is the executable available for fuzz testing. The second step is understanding the target system. As I described, here we can use a TARA, a threat analysis and risk assessment, to identify relevant interfaces and high-risk targets. The third step is to define fuzz testing strategies, as I mentioned on the previous slide. Here we need to define when to test, how long to test, what to test, and how to test, as well as how to detect exceptions and manage the test results. And finally, the fourth step is establishing a fuzz testing environment. Since testing will occur in a CI pipeline, we have to make sure that test automation is enabled and that the configuration of the tools have been made, as well as to be able to determine the outcome of test results, we need to have the proper logs generated. On the next few slides, I'll give an explanation of an example implementation using Zephyr, which is a small footprint real-time operating system, an RTOS. It's an open source software. It has built-in components and libraries for full application development, for example, device drivers, protocol stacks, and file systems. It's also designed for memory-constrained embedded devices, which makes it useful for automotive applications, Internet of Things, smart wearables, and microcontrollers. So using Zephyr as an example, we'll talk about these 4 different steps that I mentioned. The first is to understand the existing CI pipeline. Here we have daily builds where functional testing and regression testing is performed. Zephyr is running in an emulated test environment using QEMU. We also have cases where Zephyr is running as a native application on the host OS without emulation using native Posix execution. So this is interesting because using native Posix, it's possible to execute Zephyr in software only. And that eliminates the need for any architecture-specific target hardware, especially in the earlier phases of development. There are also already networking tests conducted in the CI pipeline, which includes tests for TCP, DHCP, and MQTT. Let's take a look at a simplified CI pipeline example. Here we start the process on the left-hand side. We have our prepare build environment and our build step where we download the latest sources and we build the software. In the next step, in the test step, we perform our functional tests and our networking tests. Following, in the next step, we deploy and this could be to your development environment or your staging server or production server or system, and then finally to we finish this process here in the end step. What we want to focus on here is just the middle portion here, the test step, where besides functional tests and networking tests, we want to add fuzz tests. So we can perform this as part of the CI pipeline in parallel with other testing, but add it as a separate step. So now when we understand the existing CI pipeline and how we can fit fuzz testing into that pipeline as a new step, our next activity is to understand the target system. Again, here we use Zephyr as an example, and we can see here on the right-hand side that the networking stack contains a number of different protocols. So we have from the bottom our layer 2 network technologies, including Ethernet, 802.15.4, CAN, and Bluetooth. We have a number of different network protocols, including IPv4, IPv6, TCP, UDP, and so on. And then we have our application protocols on the top, such as MQTT and COAP. Once we understand the target system, our next step is to prioritize the test targets. One way to do that is to use a systematic method to identify and prioritize these test targets using ISO SAE 21434. In the standard, there is a threat analysis and risk assessment method, TARA, described that can be followed. Also in Annex E, there are the cybersecurity assurance levels, CALs, described. CALs can be used to determine the depth and the scope of testing. So what we can do here, as you can see on the left-hand side in this table, we can use a simplified approach here using an attack vector-based approach to determine CALs. So we see here on the y-axis, we have the impact of an attack, ranging from negligible to moderate to major to severe. And on the x-axis, we have the attack vector, physical, local, adjacent, and network. So we can see that an attack that occurs over network and has a severe impact has assigned CAL 4. Whereas an attack that is, for example, physical and has a moderate impact is assigned CAL 1. So using this table, we can now assign CALs to each of the different interfaces and subinterfaces of our target system. We see this here on the right-hand side in this table. We have, for example, interface, Ethernet, Bluetooth, CAN, and the list goes on. And then we have the different subinterfaces here, layer 2, TCP, DHCP, MQTT, and so on. And then we have the attack vector as well as the impact. It's important to note that the impact would depend on where this application or where this software would run in the end. But just as an example, we have inputted different impacts here to get an idea of what can occur if an attacker is able to successfully attack that particular interface. So using the attack vector in that impact, for example, let's take a look at DHCP. We see that the attack vector is network, impact is major. We can go to our table on left-hand side. We see network, attack vector, and impact is major. Then we have CAL 4. So we can assign CAL 4 to DHCP. On the other hand, for example, Ethernet L2 is local and moderate. We'll look again on our table on left-hand side. We have local and moderate. We see that this is CAL 1. So we can now assign CAL 1 to that interface. So this helps us prioritize all the different targets in our software. In our next step now, we have to define the fuzz testing strategies. It's important to note that fuzz testing is a negative test approach, so there's essentially an infinite input space. And we have to decide how to test, when to test, how long to test, what to test, and how to test. And one way to help us answer those questions is to use the cals that we just defined on the previous slide. And with the cals, we can then align the available amount of time for testing to the different cals. So an example here shows the cal, 4 levels of cal, and we have our fuzz testing number of hours or number of test cases. So we can say that cal 1 requires 8 hours of testing or 1 million test cases, and cal 4 requires 80 hours of testing and 10 million test cases. Now these numbers are just an example and would need to be updated based on your target system and how much available time you have in your project. But let's take an example from the previous slide where we had, for example, interface Ethernet, subinterface TCP, and DHCP. TCP we had assigned cal 3, which means that we should do 40 hours of testing or 5 million test cases. And DHCP we had assigned cal 4, which means that we should do 80 hours of testing or 10 million test cases. Just to give an idea of how many test cases we could run using the Defensix fuzz testing tool, for these respective test suites for TCP, in the full run configuration, we have 9 million test cases with an average test time of 83 hours. Please note that this average test time depends on the communication workload, the bandwidth, the time it takes to process the messages on the target system, and the host PC that's running Defensix as well. And then for our DHCP test suite, we have 10 million test cases in the full run with an average test time of 93 hours. So looking at the cal at the top here, we see that for DHCP cal 4, we pretty much do a full test run here, 10 million test cases or 90 hours. Here's 80 hours and 10 million test cases. And for the TCP, we have cal 3, which means we should do 40 hours or 5 million test cases, which is about half of what this test, the full test run is. So that helps us define the strategies and how much testing that should be done for the different interfaces. Let's take a quick look at how we can detect exceptions. As mentioned, there are two approaches: in-band instrumentation and external instrumentation. In-band instrumentation, we see here an example from Defensix, the fuzz testing tool, where we can check this box to enable valid case instrumentation. For external instrumentation, we see that we can define a number of scripts that can be executed before a test case or after a test case is run to check the status of the target system. Finally, we need to discuss how to manage the test results. For example, if the target application crashes, we need to be able to restart and resume testing. We need to define how to store the test results in the log files, as well as at the end of the test run, be able to provide those results back to the CI pipeline and have some criteria where we can then determine whether we should break the build or not. And finally, we have our fuzz testing environment. So here we have Jenkins as the automation server. In the first step, it triggers a build and executes Zephyr on native Posix, as you can see here on the right-hand side. This is running on top of Linux. As a second step, it triggers to run Defensix, which is the fuzz testing tool, with a specific test plan, for example, TCP or HTTP. So we have these test plans prepared in advance. And then Defensix, the fuzz testing tool, as a third step here, will send these fuzz messages to Zephyr through the native Posix, running on the same Linux system. So all the testing is done on software. On the next few slides, we'll go through the practical steps of building the test environment for Zephyr. So first, we have to prepare the test environment. and we use the West tool to retrieve the latest Zephyr project sources. And you can see the commands here that we use on Linux to do that. We also need to install the Zephyr SDK toolchain using these commands. As a next step, we have to set up our native Posix networking environment. And the way we do that is we create this ZATH interface for the native Posix board on Zephyr. We use the NetTools scripts for the network setup to configure, for example, the IP address for the native Posix. And this is running on the same Linux host as our fuzz testing tool. So we use the NetTools here, do the setup, and then we need to have a target software, an application running that we will fuzz test against. In this case, we use the Echo Server application, and this is how we build it and run it. Now we have our target application running. We need to configure our fuzz testing tool Defensix. We set the target IP address to 192.0.22. We also can save our configuration in the fuzz testing tool as a test plan file, which can later on be executed via scripting or called from a CI automation server. We can also save the suite configurations as a settings file. What we do now is we can then execute fuzz testing using this pre-made test plan. We have the IP address configured for the target system, and we can also have different IP addresses configured in different test plans so we can run testing in parallel. Just to show you how the command for executing Defensix looks like, you see it here, where we then specify the test plan that we want to use, as well as the target IP address. And finally, once we have these previous steps performed manually to make sure everything is working, we can now add them to our Jenkins pipeline. So we will add these steps as I showed in that simplified CI pipeline earlier. We would download latest sources, we will build Zephyr, we set up our target application, the Echo Server. We then execute fuzz testing using the previously configured test plan, or we can use the Defensix Jenkins plugin and load that settings file. And you can see it here on the right-hand side. We can add this post-build action step and just configure Defensix as well as the test suite to use. So by following these steps and establishing a fuzz testing environment, we can now perform fuzz testing in a CI pipeline on software only. This allows us to also perform parallel testing. Imagine that we can spin up, for example, 10 instances of Zephyr and then perform fuzz testing on different interfaces and different target applications in parallel. This would be much more efficient than performing testing on hardware where we may have limited availability. The second thing is we also have to define how we can detect exceptions and issues on a target system. As I mentioned, if we now have control of the software only target, we can include various instrumentation where we can monitor, for example, the CPU usage or the memory usage of that target application. And this can allow us to detect any abnormal activities. The third thing here also to discuss is that while we can perform a majority of testing using software only, there are some testing that requires hardware, especially if we want to test the lower layers of some of the communication protocols, for example, on Bluetooth or CAN, then we would need to have a hardware dongle or a hardware component where we perform testing. But it's important to note that we can perform most of the testing in software and then have just a reduced scope of testing using hardware so that we can be as efficient as possible. So that brings me to the last slide with a call to action. I like to ask everyone to investigate your existing CI pipelines, analyze the target system that you want to fuzz test, define the appropriate fuzz testing strategies, and finally, build a test environment that allows you to integrate fuzz testing into your CI pipeline. So with that, I would like to thank you for your attention, and I'm happy to take any questions.